Okay, we have been discussing the mystery of CDMA. I mean, CDMA
আসসালামু আলাইকুম
looks mysterious.
হ্যালো আসসালামু আলাইকুম স্যার।
Alaikum salam.
একটা
Yeah.
কনফিউশন ছিল যে স্যার অর্থোগোনাল কোড আর কোরিলেশনের মধ্যেকার যে মেইন পার্থক্যটা এই জিনিসটা একটু যদি বুঝাই বলতেন।
Well, by orthogonality, we mean that the correlation uh, property is perfect between two different codes. And I mean, what we mean by perfect is that the cross correlation is zero. Okay. Or, I mean, just you can put it in a simple way that when the cross correlation is zero, you call it orthogonal. Okay.
স্যার অর্থোগোনাল কোডটাকে আমার ধরেন 2 to the power n পর্যন্ত তো হবে, তো এই 2 to the power n এর মধ্যে কি আমার হাফ ডিজিট +1 এবং হাফ ডিজিট -1 সবগুলা ডিজিটের যোগফল আমার 0 হবে, এরকম কি কন্ডিশন আছে কোনো?
That is what you mean by zero cross correlation. That when you correlate, the resultant becomes zero.
মানে স্যার একটা ডিজিটের মানে একটা কোডের মধ্যে যদি 2 to the power 2 মানে 4টা কোড থাকে, তাহলে আমার 2টা +1 এবং 2টা -1 হবে র্যান্ডমলি।
Uh, I mean, you need to perform the correlation bit by bit. Okay. And when you complete the whole cycle means the whole length of the code, and then I mean you should end up with equal number of ones or zeros. Okay. I mean here in place of zero we used -1, but I mean as you perform bit by bit, uh, the I mean you have I mean when you perform any bit by bit operation you get either 1 or 0, right? So just for half of them you should get 1, and for the rest half you should get 0. So you then cannot make any decision. Okay, I mean there is no correlation then between these two codes. There's see that when you have perfect, I mean, when you have correlation peak, then what do you get? You get 1 for all of them, right? You get 1 for all of them. I mean, it depends whether 1 or 0, whether you do XOR operation or XNOR operation. Okay. But anyway, it's you have in the correlation peak, I mean, assume that you have 1 for all bits. So the total will take on a big number, right? As you sum up for the whole code, it will be a big number. That is called correlation peak. Now, if you get some zeros and the rest 1, then you get lower values from the peak. Okay, once again from the beginning. That if you have, I mean, you can think of any code sequence. When you put the same code sequence and you align the two, then you have the same bits. I mean, below a certain bit, you also have the same bit state. So as you perform the operation, for every bit you get 1. Then for the whole length, if you sum up, you get the largest possible value. Okay, if the code length is say 1000, you get then 1000. Okay, just 1000 once, so you get 1000. Now, you, if you take some another code, for some of the bits you get 0, and for the rest you get 1. So now you have some value lower than that peak. Okay. So this is the particular correlation you have, whatever you get. Okay. That's the correlation between these two codes with that particular alignment. As you rotate the second code which you are comparing, then you should get some other values. Okay, so the correlation will keep changing. Now perfect cross correlation, this it's about cross correlation because you are using two different codes. When you use the same code, then it's autocorrelation. Now perfect cross correlation means that you get equal number of zeros and ones, and that occurs for any alignment. Okay, as you keep rotating the other code for all different positions, okay, you complete the whole cycle, meaning the whole sequence length you complete rotating, and for all different positions you always get equal number of ones and zeros. Okay, so you actually have the, I mean, you don't have any state. Okay, I mean, you cannot go in any direction, and that's called I mean, also that's also called orthogonal relationship. Okay.
স্যার আমার কোডগুলো হচ্ছে যদি ইকুয়াল হাফ মানে ওয়ান এবং ইকুয়াল হাফ জিরো থাকে তাহলে ওইটাকে আমরা বলবো পারফেক্ট ক্রস
Cross
কোরিলেশন।
correlation, yeah.
আর যদি সবগুলা সেম না থাকে তখন হচ্ছে ওইটা পারফেক্ট হবে না।
That's no. I mean, when you have equal number of ones and zeros, then you have perfect cross correlation,
Yes.
and that type of code you really want, you really desire for your
But
application.
sir, in the OVSF example you have shown us, there was a code like 1111 -1 -1. So both of them were orthogonal codes, right?
It's not both of them. Okay, like um, like say in a game. Okay, in a game there is a tie. Assume that there is a tie. So then you don't need to say that both sides got the tie. Okay, it's already a tie. Tie means okay, between the two sides there has been a tie. It's not about both sides tie. It's not like that, right? So similarly, you have orthogonal relationship between the two cores. Okay, so it's not about both cores. It's, I mean, they have zero cross correlation. That's why you call orthogonal. Okay, between these two, the relationship is. I mean, uh, there is uh, actually I mean, like orthogonal. What say if you take two vectors, okay, then when do you call them orthogonal? When the other vector is normal. Okay, if one vector is normal to the other, then they are orthogonal to each other. There is no component of one vector in the direction of the other vector. Okay, so there is uh, like they have no relationship.
I got you, sir.
Got it, right? Okay, thank you. So let's go back to, oh sorry, I have a different. I I forgot that I was opening our third lecture note, but actually we are with the second one. Okay. So, okay, you actually wanted me to review uh, quickly, and well, the point is with, I mean, other people will also be using the same frequencies at the same time, but they will appear like only appear like some noise, like you can assume like whiz sound, okay, but there is nothing that you can understand, okay. So when it is like that, say you may be talking with someone, but you have maybe it's raining outside, okay, or this sort of noise you have, there is some whiz sound or something from somewhere. So in that case, it's not really conflicting with what you are talking. So there will not be a major problem. However, the background noise is a nuisance. That's it. So similarly here, the other codes don't really conflict because you have zero cross correlation. But the energy they use is a problem for you. Okay, so it's like just like background noise. Or you can put it this way, that it doesn't interfere, okay, like we discussed last time, that yeah, I mean, you have some small amount of noise like thermal noise or something, okay, so the energy from other sources work like those noise, okay, work like those noise. I mean, you have some energy. But what happens when you have some interference? Okay, then that's also a direct digital transmission, and it just I mean change the property of your signal. Okay, you get you have two different types of digital information, and that just impairs the reception completely. Okay. So but here, I mean, it's not like that, okay, although other people are using the same frequencies, and for the reason we have described in the last class. Well, I need to review a little bit, like for cross correlation you get opposite types, okay, as you perform bit by bit operation for the length of the code, you get opposite states, equal number of opposite states. So you cannot decide whether it's 1 or 0. Okay, you are not inclined to any direction. Okay, so when you transmit your data, the data has to be multiplied by your own code, and uh, this it's called spreading because you're increasing the number of bits. And also after spreading, people start calling it chips. Okay. Uh, Now, when you receive, you need to know the code, and if with the right code, as you perform again the same operation, then uh, if the original bit was 1, you should get all ones. If the original state was 0 or -1, you should have all -1. Okay, so from there, if you average, you get -1, or I mean, if it was all zeros, then okay, you know that all zeros are 4. So you need, by average, I mean that since you spread by 4, you also need to divide by 4. Okay, so with -1, it's easier to explain, that it will be -4 divided by 4, you get -1. Okay, so you have a concrete decision. But I said that in reality some bits may get flipped, but nevertheless most of the bits may be on the right side, on the correct side, so you can still make the right decision. However, with the wrong code, what happens, you get equal number. Okay, ideally you should get equal number of uh, the opposite states, okay, ones or -1 you should have. So then you realize that it's not really because of some corruption, okay. I mean, it's not like you have the right transmission, but a few bits are flipped on the way. No, it's most likely, I mean, you are using a wrong code, okay, because with wrong code you should get equal number of ones or zero. Here also a few bits may get flipped, so exactly equal number you may not get, but it should be close to equal, and then that can help you make a decision. Okay, so there is some I mean, after correlation there is a step for decision making always. Okay, uh, now you cannot make decisions, so you just decide that I have a wrong code. Okay, it's not that. And we also then explain that from multiple transmissions together, it still works. And actually, the same principle you keep using. Okay, and there'll be no problem for you to detect your signal. Okay, or from your intended source. Like I have here 3 users with 3 different bit sequences for transmission, and they have different orthogonal codes. Okay, again we discussed in the last class that with 4 bits long sequence you have 4 orthogonal codes possible, right? With OVSF codes, I mean, the number of codes possible for a particular length is actually equal to the length. So 4 codes, you have 16 different variations possible. 16 variations possible, but out of those 16, 4 can comply with the orthogonality requirement. Okay, so here, in fact, out of the 4 OVSF codes, 3 are picked. Okay, they are using 3 out of 4 OVSF codes, and now you mm, just multiply the 3 different bits. Then the transmission from all of them should be summed up, and that's what you should get in the AR. And so it will be received. Now after reception, since you have 2 bits, so the codes was were used twice. Okay, again you need to put the code twice, okay, below your reception, and then perform the same operation that okay, XOR or XNOR, whatever. Well, thereafter, like before, you again perform average. Okay, like we did here. Perform average, perform average for the decision. Okay, to make decision, you perform average, and then you see you get just 1. Okay, like before, it was fully 1. It's not less than 1, because of transmission from others. It did not drop at all. So stable 1 or -1. So that's because of perfect cross correlation. Of course, if the correlation is not perfect, it should also fall from those I mean extreme values. Okay, you should get something in between. Thereafter, we demonstrated how you can generate the OVSF codes, and the term spreading factor, okay, which is a part of OVSF, um, comes from the fact that you are spreading. Okay, when you are multiplying by your code, the number of bits for transmission increase, and that increases by a factor equal to the length of your code. Okay. So we can call it a spreading factor, and that is just equal to the code length. So we showed how it is you can generate. So for 4 bits length, you have I mean spreading factor 4. Here for 16 bits length, spreading factor 4. And since you generate, always you pick one code, and from there you generate 2. Like here you had 1 1. From 1 1 you generated 2 codes. Then from 1 1 you generated 2 codes. Again from here for each of the rows, I mean just you need to put the rows, I mean the content here, in on two different rows. So each code generates two different codes with the next in the next at the next level, and that's what we are showing here. Uh, it's it's some sort of branching, and the code length increases. I mean, it's doubled uh, at the subsequent level. Okay, and also you have two uh, two branches from one. So the branching goes this way, and this way it's allowed to go down up to 512 if it is downlink, and up to 256 if it is uplink. So the spreading factor can be that big. Uh, Now it can be a question what spreading factor we should use for a particular user. Well, that depends on the requirement of the user, what application he is using, or how much the network is ready to allocate him. Like if it allocates a good data rate, okay, if to some user, it has to deprive somebody else in the cell. Okay. That's true for any technology. The overall capacity in a cell is pretty much fixed. Okay, like we discussed for 2G case, the TDMA, FDMA case showed that you have some fixed resources available in a particular cell, and it's up to you how you apportion it among different users. You can allocate a number of slots to someone, but then maybe there will be some few users who cannot access, okay, who may be waiting. So you uh, here how this it is managed. Okay, well, the data rate that you allow somebody to enjoy depends on what spreading factor you are allocating to him. You will be assigning some I mean the different OVSF codes to them. Okay, these are just different OVSF codes, and you will be allocating them to your users. Uh, but what lane do you use when you allocate? If you allocate this code, then well, with the small spreading factor 4, the guy can enjoy very high data rate. But when you allocate this one, you actually block with this code, and no further branching you can allow. None of its children can be allocated to the users, because if you allocate, then that will not be orthogonal to this allocation. Okay. Well, I mean, if you allocate children of this guy, then that children is not orthogonal with its parent, or I mean, whatever you call some grand relationship there can be, or great grand, whatever. So you block, and that's how you have to be. Uh, I mean, at the discretion of the network, it allocates, okay, depending on the requirement of different users, and depending on other factors like how might be the fairness. Okay, we probably mentioned these terms which are used to make the decision. Okay, who may get larger share of the resources and who may get smaller. So that depends on the primarily there are three factors. Uh, well, these things we would formally mention later, but right now let me just quickly write down these three terms. Okay, as you allocate the resources, among different users. Okay. So for resource allocation, the factors, I mean, it's about, I'm writing down the factors which uh, gives you uh, how you, what, I mean, relatively, who should get larger or who should get smaller. Okay, so it's about that factor. So sorry, one important thing is the fairness. The okay, then is the radio link quality. Okay, and then thirdly,
Sir, are you sharing your writings?
oh, I didn't share.
No, sir.
Oh, really? Sorry. I thought I. Oh, sorry. I forgot. Why it is not working? Oh. Okay. So the term fairness and then radio link quality of the different users. And thirdly, their data rate requirement. Okay. So there can be some other factors too, but these are the three major factors, okay, to decide how you apportion the resources. Okay. So based on that, you may give higher data. You may allow someone to use higher data rate, someone to use lower data rate, and so you just allocate different codes. Okay. Of course, I mean, yesterday you mentioned that with smaller spreading factor, well, the overall transmission rate is fixed at 3.484 MCPS. Okay. So um, if you use lower spreading factor, the actual information can have a higher rate. Um, Now, I said that the voice typically uses 128, but it can also be 64, or I mean, it's not fixed at 128, but most of the voice calls have 128 spreading factor. And similarly, the data transfer can use many different spreading factor. But if I calculate the rate for say spreading factor 8, okay, then what do you get? The okay, again, oh, we go back to oh, I not sure how we can clear the whole thing. Actually forgot. Is it the eraser? No, I forgot which one is the eraser.
So maybe the red one from the left.
Okay. Yeah. Okay. So your info data rate has to be multiplied by spreading factor, and then you get the actual transmission rate, which is held fixed at 3.84 Mbps. So if your spreading factor is 8, your data rate will be like, but here this one is symbol rate. Okay. So that symbol rate will be now for UMTS, it is always QPSK. It supports only QPSK. Okay. So you have 2 bits per symbol, meaning that the data rate in BPS will be 3.84 into 10 to the power 6 divided by spreading factor, right? So now you can calculate for any spreading factor, okay, like they did for spreading factor 8. Okay, I mean it's 960 kbps, okay, for spreading factor 8. The symbol rate is 480 kSPS. The BPS, okay. Now, if few things I will mention here for EMTS, because similar concept or similar processes, okay, I'll talk about a few processes, and they apply to some apply to the symbols which are organized in the time domain in a particular way. So I'll mention it for EMTS because similar, uh, almost I mean in a very similar way it is done in the case of LT. Now you have some 10 millisecond radio, 10 millisecond long radio frames in EMTS. LT has the same. It is also called radio frame in LT, and the length is also 10 millisecond. So within that 10 millisecond, you keep sending your symbols one after another, and so actually you have 38,400 chips in 10 millisecond in every radio frame, because I mean 3.84 mega chips you send per second. Okay. Now within this whole length is again split into 15 parts, okay, and they are called slots. So you have 15 slots in one radio frame, and you have then 2560 chips per slot, because I mean just divide this 38,400 by 15. You have 2560 chips per slot. Okay. Okay. So it's shown here. Okay, the slot length will be 0.6 millisecond. Okay, and in the slot, the number of chips are fixed. Okay, it is always 2560, but the number of actual your symbols, actual your information symbol, okay, will depend on the spreading factor. Now, probably it's clear that you can support multiple users in the cell together, which is the way you multiplex. Okay. But we still have a big question left. Okay, it didn't solve the whole mystery. Your cell may have just maybe may have 100 active users, and the operator has list 5 megahertz. So a particular cell is using this 5 megahertz. But what about other cells? You don't buy any additional frequencies for the neighboring cells. In the case of 2G, we showed that you have you need to split the frequency to make sure that the neighboring cells don't interfere. You use different frequencies in different in a neighborhood. Okay, the adjoining cells shouldn't use the same frequency because that would cause interference. Now we can get rid of interference within the cell, although you're using the same frequency. That has been explained so far. But what about the adjoining cells? You don't have any other frequencies available. So you have to use the same frequencies. All the cells also use the same frequencies in the whole nation. So then how you manage? Okay, the OVSF code tree itself has some limited number of codes, right? So even if you go to 512, that will of course come with a lot of sacrifice of data rate, right? We know how to calculate the data rate. Just 3.84 into 10 to the power 6. Oh, sorry, I didn't multiply by 2. There's a mistake. You have to multiply by 2. Okay, because in QPSK you have 2 bits per symbol. Okay, for symbol rate you don't multiply, you omit this 2, but for BPS data rate, bit rate, you need to multiply by 2. Okay. Anyway, so with that we know that if you increase the spreading factor to 512, the data rate will be very small. But even with that small data rate, even if we consider that satisfactory, you have only 512 users. In the whole nation, you can support only 512. That's never, that's not how it can work. So still mystery remains. Now let me straight go to the answer. There is another level of another level of application of correlation. Okay, so there are 2 separate processes. We have discussed spreading so far with the use of OVSF code. So another PN code is used, and there is another level of similar process, and it is called scrambling. It is not spreading because another spreading will be luxurious, will actually be too luxury to get adopted. We cannot have another spreading that will cause the data to fall to too low value. Okay, So no further spreading we can use. What is done here? Another PN code is used, and say for downlink, every cell has a particular PN code for the use of the downlink. So for all users in the same, it uses the same PN code here for this second process, second level of process. And in this process, it does not spread or it does not increase the number of bits. What it does, it takes the whole radio frame. So 38,400 chips, or actually it's just like bits. Okay, it takes that whole length that you have got after spreading. Then it puts the PN code, and thereafter it performs a complex operation, which between your desired bit sequence and your particular PN code. A complex operation it performs, and that operation generates again a sequence of the same length, again 30,400. Okay, like I may just draw here. What is that? For every radio frame, it performs the scrambling operation. One after another, every radio frame is taken. So this is what you have got after spreading. So this is your data. Okay. Then you take again your, another PN sequence, another PN code I can write down. Okay. So it's also 38,400 bits long. Okay. Thereafter, it performs some mixing operation, which generates again some data for transmission, data for TX, again with the same length. Well, this is done for one particular cell, say cell 1, okay, and then you have another cell, cell 2, just next to cell 1. In that cell, we are talking about downlink for now, okay, downlink operation, scrambling for downlink. Okay, so the PN code here, if it is 1, for the second cell, the PN code will be different. PN code will be different. Okay. So again, you use your data. Okay, maybe your data and PN code. Okay, so you get some. Okay, this is for transmission. Okay. Well, now these PN codes have some good cross correlation property, not perfect, the cross correlation property between the PN codes 1 and 2. Okay, the cross correlation property are pretty good. Okay, it's not perfect. And another, I mean, some orthogonal, I mean, PN code with perfect cross correlation or orthogonal relationship is not possible here. Rather, I mean, some cross correlation which is very good. Okay, so that is used, and thereafter the data you generate after the operation, the mixing operation, or which is called scrambling operation, generate some data which change the correlation property and brings the correlation property close to what you have in the PN code. Okay. Again, here you have the data for transmission which has some correlation property close to what you have in PN code 2. Once again, the data that you transmit in cell 1 in downlink, okay, will have some correlation property close to what you have in PN code 1. Similarly, in cell 2, it will be close to what you have in PN code 2. Now, for any user, I mean, is the same PN code 1 in cell 1 or is the same PN code 2 for cell 2. But all these different transmissions in cell 1 have some correlation property similar, okay, close to PN code 1. And in the cell 2 is close to PN code 2. So there is a difference. I mean, if you are receiving signal from both uh, because of your location, you may be located here. You see, you are the UE here, and there are 2 base stations. Okay. Maybe the second base station. So sometimes it gives some delay. Okay. So BS1 is little closer. You are within the cell from BS1. Now, from cell 2, from both the cells, you are receiving data, receiving signal, okay? But you should be able to distinguish because of pretty good cross correlation. Okay. Well, the second thing is that from BS2, the signal should be weaker than BS1. So you have some better or stronger signal level from your desired base station. Now, although BS2 is using the same frequencies, but its transmissions has some correlation property with which you can reject to some good extent, because I mean your desired signal. Okay, like I said that when you have 2 people in a party, 2 pairs in a party, talking with languages pretty close, then it will be little problem. Like say, I mean your partner is talking in Bangla, and someone else around you is talking in a language close to Bangla. Okay, then that can cause some difficulties. Sometimes it may get jumbled with with what you hear from your partner. Now you assume that, please pay attention to me. Now please you just visualize that your partner says little loudly, and the other guy who is speaking in a language and you don't want to listen to him, but that language is close to Bangla, but his sound level is lower. then it will probably not be a big problem. You can still detect or recognize what your partner is saying. Okay. Exactly the same way, you want to reject the uh, signal from BS2 because you are close to BS1. There will be the correlation relationship is not perfect here. There's no provision for making it perfect any longer. Okay, we don't have that luxury. But it's pretty, but correlation property is good. Okay, there is some level of difference, some good level of difference between them. On top of that, the signal from the unwanted source has a lower value, and you have an upper hand from the signal level. So you should be able to recover the signal or the digital information from BS1. Okay, so the correlation strength together with the signal, uh, the relative signal strength, okay, helps you determine the transmission from your particular source. So the transmissions from other cells, okay, can also use the same frequencies, and that's what they do. Okay. So this is called scrambling. Now the exact procedure for scrambling is not fixed. It's a long process, first of all, and secondly, it doesn't have a fixed procedure. Like in the case of uh, OVSF code, we already explained what the steps are or how you spread. Okay, so it's a straightforward procedure, but here you have a complex procedure, and it is not also a fixed procedure. Okay. Now in the downlink, as I said, that every cell uses a fixed code. So that code is called primary scrambling code, or PSC. Okay, see the term primary scrambling code, or PSC. And there are just 512 PSCs possible, no more than that. Okay. Now you need to make sure that you don't listen from two cells with the same PSC, because between cells you differentiate using PSC. So if it happens that, just think of the situation that your cell and your neighboring cell are using the same PSC. I should put it this way, that the OVSF tree, okay, first of all, for our orthogonal use, you have a OVSF code tree. This whole code tree is used in every cell, or every cell repeats the same OVSF code. There's just one OVSF code tree possible, and every cell uses the same OVSF code tree. So within a cell, the different users are multiplexed using OVSF codes. But between cells, you will have the same OVSF codes repeated. Say, for example, this particular code you may have been allocated in your cell, but this code has been also allocated to somebody else in the next cell. So how you differentiate? So that's why you need this second level of procedure. Now, as I said, that the difference, say in the downlink, every cell is is a particular code. Okay. So this code can be regarded as an identity of that cell, because at least at least to a certain level, it can be considered an identity. It's because in the next cell, you cannot repeat the same code. And then, the same OVSF codes will be used. So if these scrambling codes are also same, then of course you cannot differentiate any longer. There's no way you can separate. So the OVSF codes has to be different. The scrambling codes have to be different. Okay, but if at a far distance, maybe after say 1000 kilometers, you can use the same scrambling code. That cell will be again using the whole OVSF code tree, but energy will not come to you from that cell. So there is no harm if you repeat the scrambling code there. So the scrambling codes cannot be repeated in the close vicinity or in the same neighborhood, but at a far distance it can be repeated. And you should repeat to limit the number of scrambling codes. Otherwise, you need too many. So unnecessarily, you don't increase the number of scrambling codes. So it is just fixed at 512. In fact, the radio planners know that if you want to make sure that the signal will not get repeated, okay, then how many unique numbers you need? It is actually some value around 500. Okay, that's safe enough. It is safely high. So with it's held, it's taken 512 here. So 512 PSCs are, so that makes sure that the PSC you repeat at a distance which is far enough. Okay, or there is no chance that signal will come to you from there. Okay, 512 or a number around 500 is good enough. The scrambling operation is actually started with CDMA, but it's this part is used also in 4G. You don't have the previous part like the use of orthogonal codes or CDMA, but the second stage scrambling operation you still have, because with no additional cost you can bring some level of differences, right? Since you are not increasing the length of the bits or the number of bits, you are not increasing. Like we said, we had 30,400 bits long frame, okay, and we keep the same number of bits, but we still create some level of some property which can cause some level of separation. You can more easily separate two different transmissions. So with no additional cost, you can do that. So that's why the scrambling operation is also used in 4G or 5G. However, there is also some cell identities here this way. Okay, but well, I don't. Okay, what I want to put the number here PSC is considered some identity, because when you first power up your device, you need you need some level of identity from the base station to distinguish transmission from many different base stations. You have signal from many different base stations, and then you need to separate them and then listen to a particular one which may have the best energy level, the highest level. So at this level of operation, you haven't yet been able to read the detailed messages from the base station. You have just powered up. Okay. So at this early stage, there should be some primary leveler or something that you're using in the physical layer, or just what you use along with your transmissions bits. Okay, you need to have some technique there, to separate cells different cells or different base stations. So that is what uh, you have for PSC. So the all transmissions are scrambled with the PSC in the downlink, okay, in a particular cell. The same PSC is used for all different downlink transmissions. So as you power up, you listen to the transmissions from different cells, and then just with the, we'll show, we'll have a long discussion in the next class to show you that you just check which particular, and you can find out which particular PSC you have for a particular transmission. So you may be hearing from 10 different base stations, but for all of them you can find out PSC, and then you come to know that I have actually signal from 10 base stations. Okay. Otherwise, how could you do that? Everybody is using the same frequency. So just using PSC, the UE distinguishes the transmissions from different cells, and then it also, after it distinguishes, it compares the signal strength from the different cells, and then it picks the best one, the one which has the highest level of signal power. Okay. So, but before it compares, it has to first separate. It has to separately identify transmissions from different cells, and for that purpose, it uses PSC. Okay. So, in the downlink, PSC works as an identity of the cell, of a particular cell. Now, in the case of uplink, well, in the uplink, there are many different users, and the users are mobile. In the downlink, the base stations are not. Okay, the base stations who transmit in the downlink are not mobile. They have a fixed position. Okay. So the coverage area is fixed for a cell, and every cell has a particular PSC. It's not actually from the base station level, which is called node B. It's at every cell you have a certain PSC. So fixed coverage area, geographical coverage area, works with the fixed PSC. But in the uplink, users are mobile. They change cells and their uncertainties. So what is done here? Every user is given a different, some unique code. The pool size, the allowable pool size for scrambling code is made larger here, and you can, it's so large that the network allocates just different codes to different people. The most likely the code will not match with anybody else, even in the whole country. To make it like so wide, okay, because the users are mobile and all that. It's the pool. The possible number for the course is made almost close. Almost 17 million. Okay, 2 to the power 24, which is close to 17 million. So each UE is assigned a unique code for uplink transmissions. Okay, so the base station in a cell will listen from, say, 10 different cells from users located in 10 different cells around itself. and there are maybe 100 users in every cell. So you have 1,000 different users, okay, around yourself from, yeah, I mean, from particular base station. So unlike the downlink case where you are listening from a few base stations, you have some fixed base stations, maybe from 10 different base stations. Okay, the base station listens from say 1,000 users, and the I mean, if you have matching in codes, okay, the spreading scrambling code, then there are chances of problem. Okay, I mean, so what is done? It's you have a really vast pool size, and all these 1,000 users will practically get different codes or unique codes. So the base station listens with different codes from all users. Well, then again you have some good level of cross correlation property, and so it will be able to distinguish. Okay, so probably it's sort of clear why in the uplink you need so many codes. Okay, now in the downlink you call it primary scrambling code, but there is something called secondary scrambling code, which most usually it's not used. Okay, and when it is used, it has a different purpose, not even related to what we discussed here. The purpose of PSC and SSC are completely different. But it won't be worthwhile to discuss SSC because there are many different important things in EMTS which we are not skipping, which we are not discussing. We'll rather discuss LTE or 4G, 5G, these things in detail. Okay, so now, in the next class, I will discuss synchronization, a procedure with CDMA. Well, this whole thing I wanted to finish this week, but I couldn't. So in the next class, inshallah, we'll also have some. A part of the next class we'll use for LT, okay. But the first part we will use for the discussion of synchronization with UMTS. But before I do that, let me show you a few different steps in the physical layer. Thus, LT also uses similar steps, similar processes in the physical layer. It's probably not clear enough. Okay, check from the bottom. You have QPS modulation. Okay, I said that is always QPS. But before that, you have this PN scrambling. Okay, the scrambling operation. And before that, you have OVSF, the spreading. Okay, so these are the bottom processes. Then before that, you map your data to the physical layers. Okay, so there are some upper layer procedures like say coding. We discussed coding. Okay, so you have coding, and then after coding, you want to fit in say the radio frames or something, but the number of bits generated does not exactly match say the 38,400 chips requirement. Okay, so you, for the matching purpose, you do if either you may have to add a few bits, or you may have to, there are a few things that you can do, like you have got this many bits, okay, after coding, but to fit in the radio frame size, you need this many bits. So what you may do, a few bits you may just repeat. Okay. Or sometimes you may drop a few bits, just expecting that even without these bits, it will be able to recover. You have coding and other things. And sometimes what you can do, well, you send some additional bits, but with no power on them. Okay, because you need only, I mean, these are the only necessary bits. So use power for your necessary bit transmissions. But to fit in the size, you need additional bits. But since there is no really information you have there, so don't use any power. Okay.
Sir,
So this sort of steps. Oh,
yeah,
time is up.
yeah.
Time is up.
So we have a class.
This whole thing is called rate matching. Okay. Yeah.
Sir, about the lab, inshallah, we will be having our discussion with Nafis sir tomorrow, and I don't know if the other teachers will be there. Sir, as per our feedback from the last semester, when you took our lab classes, it was convenient for us to have the pre-recorded lectures for the lab experiments, as many of us suggested. And because in the lab we could see on the projector and then we could simulate in our PC or laptop. But when we do have this live experiment classes is that we have to swap between Zoom and experiment at the
Right.
same time. So
Hmm.
it's a big problem, and also the
Right.
connection issues. So
Right.
uh,
I'll talk to Nafis. Uh, I'm not. I haven't been assigned this particular lab course, but I'll be in touch with the guys who are conducting. Now, let me tell you what they're planning to do tomorrow. It will just be a startup, uh, and sort of. We haven't yet discussed anything from LT. So the fruitful things, or I mean the concrete things that we can do for our lab classes, we will do. We start doing after say 2 or 3 weeks. Okay. So uh, in this week they will sort of repeat uh, something from our last semester. Remember that when we did atoll, the major part simulation we discussed, but not. I mean, there was some we shortage of time. We had some rush, and it was not explained very well. And also, we got some examples which did not fit in, or which were not. I mean, perfect for proper explanation. So I mean, what we planned that Nafij will explain only the simulation part, but in a more elaborated way from Atoll. And so, just as a startup, that will probably not be useless. Okay, uh, you get. I mean, it was not. It might not have been enough clear in the last semester. And secondly, we have to manage our lab classes within the semester, considering whatever limitations we have. It's still uncertain when we may be able to go back to physical classes. We need to do some experiments using a hardware setup that we have purchased recently. It's a LT base station. Okay, although it is not yet activated, it's giving some trouble. Okay, after we received it right before the lockdown, but the supplier didn't have complete support, and so we are trying to resolve that. And because of lockdown, I mean, the personnel couldn't come in anyway. So that will probably be resolved, and we'll do some experiments with the base station, but we cannot do here until we go back to physical classes. but it's uncertain when we can do that. So I think we should have planning to do experiments using software, and in our plan it should be uh, I mean self-contained, or it should be self-sufficient for the whole course. Okay, and of course when you get a chance we'll do that physical experiment with that base station. So this is why we are trying to sort of like rate matching, you know. I mean, we are discussing the rate matching that you repeat when you want to fit in the size. Okay, it's sort of like that. Okay, sort of that repetition, but probably it will be helpful to some extent. Okay, uh, and the radio planning tool is really a strong, I mean, an important part of cellular communication. Unfortunately, we cannot have some licensed radio planning tool. Okay, it's not possible. So I'm using a cracked version. I mean, this atoll is sort of, it's a little bit old, but at least, I mean, one kind of radio planning tool we have. Okay, to some extent, we can feel how it might work. Okay, so it will be good that you get better idea with the tool. There is no other radio planning tool that we can really manage for this lab. Okay. So, but other experiments will not be repetition. Whatever we do, they will be not repetition, and they will be something that we should really do. Okay, like we have got a simulator for LT physical layer that we will try to demonstrate, and we'll be doing some experiment with XCal. Okay. So tomorrow it will just start up, but I will talk to the folks and I'll request them to have some pre-recorded demonstration. But for tomorrow you don't need that, right? Do you?
Sir, I think
No, sir.
tomorrow
No,
is
sir.
just
I
an
think
introductory
tomorrow
lab.
we can have an intro, as our many of us will have the clear idea about how this course will be taken.
Yes, sir.
An intro of 15 or 20 minutes, as Nafis sir said.
Yeah. I mean, if I understand you correctly, I mean tomorrow you don't need the pre-recorded lecture,
Yes, sir.
right? Yeah.
So
Okay.
Nafis sir
But
said I
from
think tomorrow was the introductory lab for 15 to 20 minutes about how we will conduct the lab.
oh really? Okay. I thought they would also demonstrate at a
Yes,
little bit.
sir. It would be also a demonstration, as he mentioned in the
Okay.
classroom, to be ready with Atoll.
Okay. 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 But for other experiments, yeah, well, inshallah, we'll have some pre-recorded lecture. Okay.
Inshallah.
Inshallah, we'll have that. Okay. I mean, they will have that. I will request them to do that. But you know what? When we work with XCal, I plan to participate. Okay, in person. Okay, I mean, uh, directly, inshallah, I'll be a part of the lab class.
Sir, inshallah, when will you join us for the XCal experiments?
Uh, I I just think it worthwhile to do after we progress our course theoretical discussions to some good extent. Okay, because we'll be explaining the messages, and you should have some prior idea about what they are for. Okay.
Okay, sir. So, sir, can we leave then?
Yeah, yeah.
Okay,
Thank you
sir.
for your
Assalamu
time.
alaikum, sir.
Walaikum assalam. Walaikum assalam.